Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 2. In the module 8, we will be studying about aryl halides and phenols. In the lecture 1, we will be studying about preparation and reactions of aryl halides. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by TTS Swayamprabha, MHRD, New Delhi. In this session, the topics that we will be studying include preparations of aryl halides. Basically, we will be studying about the direct method of preparation of aryl halides. Then we will be studying about aryl halide preparations from diazonium compounds and then Hunt-Sticker reaction. So these are all the reactions we will be studying about the preparation of aryl halides. We will also be studying about reactions of aryl halides. In this, the main focus will be given to aromatic nucleophilic substitution. We have a couple of mechanisms, which is addition-elimination mechanism. Another one is elimination-addition mechanism or the benzene mechanism. We will be studying this, and we will also be studying about comparison with aliphatic nucleophilic substitution and aromatic nucleophilic substitution reactions. In this session, we will be studying about preparations of aryl halides. So there are three methods are there by which we can prepare aryl halides. The first one is direct halogenation method. Then we can also prepare aryl halides from diazonium salts. And the third method is by Hunt-Sticker reaction. So let us look at the first one, which is the direct halogenation. So the direct halogenation is basically the aromatic electrophilic substitution reaction. So in this reaction, what are the requirement is for the reaction to carry out, we need a Lewis acid catalyst. So by simply mixing the aromatic and the halogen both together does not give the product. We need a Lewis acid to catalyze this particular reaction. But there is a major limitation for this reaction. So this actually leads to polyhalogenation. Although direct halogenation is a good method, depending on the condition and the temperature used, we may end up with polyhalogenation. So it is little bit difficult to control monohalogenation of aromatic systems. Then there is another important thing, which is the substituent effect. Basically, electron donating substituents favor these kind of aromatic electrophilic substitution reaction. That is, the direct halogenation is favored by electron donating substituents, and this reaction is hindered by electron withdrawing substituents, because the electron donating substituents give more electron to the aromatic system so that it is ready to undergo electrophilic substitution. But the electron withdrawing group simply pull the electrons away from the aromatic ring, so the aromatic ring itself becomes electron deficient, so it cannot undergo aromatic electrophilic substitution very effectively. So that is the reason these two groups have different effect on the direct halogenation. So let us look at the mechanism for this reaction. Basically, here for our convenience, we have taken benzene as the starting material, and halogen is basically chlorine or bromine. We will see why iodine or fluorine cannot be used soon. So in this particular case, the direct halogenation, the reaction halogen used is mainly bromine and chlorine only. So in the presence of iron is here the Lewis acid catalyst, which is being used. gives the corresponding aryl halides and HX is produced. Now the big question that will be asked is, iron is not a Lewis acid, so then how this reaction will be facilitated by this iron? Because iron is in the zero valence state, Fe is 0. So that means this is not the Lewis acid, that the catalyst which we have been talking so far. So how do we know the iron Lewis acid catalyst is formed? So in the mechanism, what happens is the zero valent ion is converted to the active catalyst. The Lewis acid catalyst is generated in situ. So this is the initial step that happens. So 2 iron reacts with the 3 halogens to produce 2FeX3. So preferably the halogen used is either chlorine or bromine. So the iron trihalides are produced in the first step. So this is the catalyst that is produced in situ. So once this catalyst is formed, this will further undergo reaction with the halogen. So as we know, this is a Lewis acid. Lewis acid means this is electron deficient basically. Iron has vacant d orbital. So the halogen, which is having lone pair of electron, donates its electron to the iron. And these donated electrons are basically kept in the vacant d orbital. So that is why the iron gets a partial negative charge, because the halogen, one of the atom in this particular XX bond halogen, gave its lone pair to the metal. This becomes electropositive, or this becomes a positive ion. But this positive ion cannot be stable for a long time. So what happens is, this pulls the XX bonded electron towards itself, thereby generating a X plus ion. So the X plus ion is the actual electrophile which is involved in this particular reaction. So once the X plus ion is formed, so this X plus ion is now attacked by the pi electrons of the aromatic system, because this is the electron rich system and the X plus is the electron deficient system. So the pi electrons are now bonded towards the X plus, which leads to a intermediate as shown here. So this is the slowest step or the rate determining step for this particular reaction. So since the X plus is added to one of the carbon, the neighboring bond, this bond is actually bonded towards the X plus. So the adjacent carbon becomes a carbocation. So this can be stabilized by the pi electron from the next double bond, and this also can undergo resonance structures. So we can write common resonance structures as shown here. The aromatic ring is having the positive charge, and the chlorine and the hydrogen are attached to the carbon. So now this H will be abstracted by the X which is present in the catalyst. So the X and H forms a bond which leads to the hydrogen carbon bond being shifted towards the aromatic ring. So by that, this is not a stable aromatic system. The 6 pi electrons are not present in this carbocation intermediate. By the loss of this proton, it will regain its aromaticity. So that's how we can get the final product as the substituted product, that is the haloarene is formed. Here for the convenience I have put as a chlorine, so it can be chlorine or bromine, and FeX3 is regenerated in the last step. So this is the catalyst which can further undergo the same cycle of reactions together, and HX is the byproduct formed in this particular reaction. So this is how the direct halogenation leads to substituted aryl systems. As we mentioned, there are few limitations of direct halogenation. We saw polyhalogenation is one of the limitations. We will also see what other limitations are there for this particular reaction. See, the first and foremost thing is the reaction requires dry conditions. That means there should be no moisture present in this system. Otherwise, it will deactivate the Lewis acid catalyst. So for this reaction to be successful, we need to use dry solvents, and the reaction conditions has to be extremely dry. And the second, as we mentioned, the mixture of mono, di and tri halogenation is possible, that is polyhalogenation is possible. And another major drawback for this one is fluorination and iodination is very difficult to carry out. In other words, generally direct halogenation does not give aryl fluorides and aryl iodides. And the last important thing is, in the absence of the Lewis acid catalyst, that is the in situ generated Lewis acid catalyst, if it is not formed in that reaction, then the reaction becomes very slow. So these are all the major limitations of direct halogenation method. Now the next question is why we say iodination is not possible. That is why iodination of aromatic compound is very difficult. And if at all we have to make the iodo derivative, can we really do it? So let us see whether it is possible or not. So the major problem is in the direct halogenation, the side product formed is basically, if it is iodine, we will be ending up with a hydrogen iodide. If it is chlorine, we end up with a hydrogen chloride. If it is bromine, we get hydrogen bromide. Similarly, if it is iodine, we get hydrogen iodide. But unfortunately, hydrogen iodide is a very strong reducing agent. So what happens, even though the reaction proceeds as the normal case, like benzene in this particular case reacts with iodine in the presence of a Lewis acid to give the iodobenzene and HA. HA being a strong reducing agent reduces this iodobenzene back to the starting material. So that is the reason we do not get the maximum yield of the iodobenzene in this particular reaction. So if at all we have to still make iodobenzene, can we use it? So there is a different method we have to follow. If somehow we can remove this HA from the system, then that may facilitate the formation of this iodobenzene. So what is the way to remove this hydrogen iodide? The simplest one, the most effective one is oxidation. So if we can remove the HA by oxidation, that is a mild oxidizing agent, if it is used in this reaction, that will convert the Hi into I2. So I2 is again the starting material for the formation of the iodobenzene. So in this particular case, we can effectively prepare the iodobenzene. So although we say iodination, direct iodination of aromatic system is not easily possible, but by the use of a mild oxidizing agent, it is possible to make iodobenzene also. Now the next method is from diazonium salts. So basically the diazonium salts are not readily available because they are quite unstable. So we have to prepare in situ only. And moreover, because they are unstable, it is very difficult to store them for a longer time, and they are generally prepared from amino compounds. So these are all some of the limitations of diazonium salts. So basically how the diazonium salt can be prepared is given here in the following scheme. So the benzene on nitration with the fuming nitric acid and sulfuric acid produces the nitrobenzene. So here generally we end up with the mononitration. So once we get the nitrobenzene, it can be reduced to the aniline. So once we form the aniline, that is treated with nitrous acid at low temperature, basically at 0 degree centigrade, produces the diazonium salt. So this is always N2 plus ion is present. So this is what is the diazonium salt that is formed in the reaction. This diazonium salt can be reacted with BF4 minus to make the fluoro derivative, that is fluorobenzene can be prepared using this method. If we use copper chloride or copper bromide, we can get the chlorobenzene or the bromobenzene respectively, and Ki can be used to prepare the iodobenzene. So in other words, the diazonium salt method, even though the diazo compounds are little bit unstable, this diazonium method actually leads to the formation of all the 4 halogen derivative. So this is the most preferred method for the preparation of aryl halides. Now let us look at what are the major advantages of the diazonium salt method. Now as I mentioned, the fluoro and iodo derivative can be prepared very easily. So this is one of the better method rather than the direct iodination where we use oxidizing agents. Because even if we use oxidizing agents for the preparation of iodobenzene, the reaction requires Lewis acid. In other words, dry conditions are still required for that particular reaction. So that is the major limitations. Whereas in the diazonium salt route, we don't have to follow the extremely dry conditions. And another major important thing is diazonium salt preparation always gives mono substitution only. And the major since it is giving a mono substitution, there is no poly halogenation possible in this particular case. In other words, we can also make the required single isomer when other methods fail. Basically, for example, if you take toluene, toluene is an activated aromatic system, and use of toluene for the preparation of aryl halides by the direct halogenation method always gives trihalogenated toluenes only. So that is a major limitation if the aromatic system is activated. Whereas in the case of diazo route, we can very well selectively prepare only the orthobromotoluene, and in this particular case we never get polybrominated systems are possible. So this is one of the major advantage of using diazonium salt method. Then the next one is the Hunsticker halogenation method. Here a carboxylic acid is converted to the silver salt with the help of silver oxide, and this on treatment with bromine produces the corresponding bromo-aryl derivatives with the formation of CO2 and silver halide. Whatever is the, if we use bromine, we end up with a silver bromide. If we use other halides, we end up with other silver halides. Now let us look at the reactions of aryl halides. The first one what we will be studying is the aromatic nucleophilic substitution. So in this reaction, chlorobenzene is treated with sodium hydroxide at 350 degrees centigrade produces phenol. So the chlorine is replaced by OH minus. So the leaving group is halogen and the nucleophile is OH. And if you have a paranitro derivative, that is the paranitro-chlorobenzene, then instead of a high concentration of sodium hydroxide at high temperature, we can actually use 15% of sodium hydroxide at 160 degrees centigrade. That is roughly half the temperature for the unsubstituted system. So this gives the corresponding phenol. And if there are two nitro substitutions, that is 2,4-dinitrobenzene, chlorobenzene, even sodium carbonate can be used at 130 degrees centigrade. We don't have to use a strong base, that is sodium hydroxide is not used. Of course, this is the aqueous base we are using. So the OH is coming from the solvent water molecule. That gives the corresponding phenol. And if you have the trinitro derivative, even water is sufficient to carry out the aromatic nucleophilic substitution. So overall what we can say is electron withdrawing groups actually activates the aromatic nucleophilic substitution. We have earlier seen the aromatic electrophilic substitution is deactivated by the electron withdrawing group, but aromatic nucleophilic substitution is enabled or activated by electron withdrawing substituents. Welcome to the next session. In this session, we will be looking at aromatic nucleophilic reaction. What is an aromatic nucleophilic reaction? when a nucleophile adds to the aromatic ring, that is basically the substitution of X with a nucleophile is called nucleophilic substitution reaction. And when it happens in the aromatic ring, this is called aromatic nucleophilic substitution reaction. In this reaction, the leaving group X leaves with its own electrons. The nucleophile comes and attacks the aromatic system to form the final product. Two types of reactions. Basically, the reaction occurs via addition followed by elimination. This happens when there is an electron withdrawing group present in the aromatic system. The leaving group is either ortho or para to the electron withdrawing group. This type of mechanism occurs. There is a second type of mechanism that is called elimination addition mechanism. This happens when there is a electron donating group is present, and it also requires a strong leaving group and requires very harsh conditions. So in the addition elimination mechanism, what happens is the nucleophile comes and attacks. They form an addition complex first, and then the leaving group leaves. So this is what is called addition elimination mechanism. So basically the last step is when we do the charge reversal, that leaves the leaving group and the aromatic system again regains its resonance. But there are some problems associated with this kind of mechanism. Let us see what are the problems associated with this mechanism. Now, when the nucleophile adds, the system loses its aromaticity. So we are having an intermediate which is non-aromatic. So it is a very difficult process in which the aromatic system loses its aromaticity. So that is the reason this type of reaction does not occur. That means the nucleophile adds first, and the nucleophile and the halogen both are in the system. Then finally the nucleophile leaving group leaves. So this kind of mechanism does not occur. Generally in the Michael addition reaction, which we will see soon, this kind of reactions occurs. But in the aromatic system, this kind of substitution reaction does not occur. So let us look at the reaction very carefully. So how this reaction can happen? We do know para-chloronitrobenzene, when treated with 1 ml of sodium hydroxide at 150 degrees centigrade, does give a phenolic compound. This reaction occurs but under very high temperature and a very strong base. The system has only one electron withdrawing group, that is the nitro group. If we take two nitro groups in the same aromatic ring, this substitution reaction occurs at a lower concentration of the sodium hydroxide, that is 1000 times lower concentration, and the temperature is also 50 degree lower. So this is not a very harsh condition like the previous one. But when we have the trinitro substituted chlorobenzene, the reaction occurs with simple water itself at 40 degrees centigrade itself. So this is how this is happening. We will just look at each step very carefully. The chlorine is the leaving group, OH is the nucleophile which comes from the sodium hydroxide, and nitro group is the electron withdrawing group. So the minimum requirement for this type of mechanism is the aromatic ring should have at least one electron withdrawing group. So let us look at the step-by-step mechanism how this reaction occurs. So in the first step, what happens is the nucleophile OH minus adds to the aromatic system and the halogen leaves. So during that time, the charge separation actually occurs. The charge separation is stabilized by the nitro group. And then finally the OH is attached and the chlorine leaves. So this is what is the substitution occurring at this carbon. The stabilization of this intermediate is not very high compared to the second dinitro derivative,
where the negative charge is spread over lots of place. And in the case of trinitro derivative, it is even more facilitated. The charge distribution occurs throughout the aromatic ring. So this reaction, the substitution reaction, occurs very, very easily. And how do we know this reaction actually occurs? We will see the complexes, how these intermediate complexes are actually isolated, and then the mechanism was actually proven. So in the trinitro derivative, when R is either hydrogen or O methoxy and the metal is basically potassium or sodium, the alkoxide ions, whenever they are being used, these kind of Meitner-Heimer complexes are actually isolated. So they have a M plus charge followed by the negative charge remaining on the aromatic system. And the charge distribution occurs over a large area. So that is the reason this complex is a stable complex and people had actually isolated. So in this complex we have the group R is already present, as well as the OR group is also introduced. So that means the nucleophile is also present, the leaving group is also present in the presence of the metal ions. So this complex that is being isolated proves this kind of addition elimination mechanism occurs. Elimination addition mechanism. We had so far seen the addition elimination mechanism. Now we will move on to elimination addition mechanism. So the major difference between the previous one is the elimination occurs followed by addition, and this requires a strong leaving group and also requires very harsh conditions. There is a major difference between addition elimination and elimination addition mechanism. In the previous one, wherever is the leaving group, there only the nucleophile adds. But in this case, there is two possibilities. Say for example, if you take this toluene with parachloro, when we treat with sodium hydroxide at 350 degrees centigrade, that is extremely high temperature and a strong sodium hydroxide basic conditions, the substitution of the halogen with the phenol, that OH, happens. But then here we have two isomers. There is one isomer which is having the para substitution. There is another isomer which is the meta substituted one. So in this elimination addition mechanism, what happens is most of the time we end up with a mixture of products, and we will see why we are getting a mixture of products in the mechanism of this reaction. When bromobenzene is treated with sodamide, we get aniline, and again the temperatures are under liquid ammonia conditions at minus 33 degree. And for the anisole derivatives, the chlorine is actually replaced. See, if you look at the starting material and this product, the chlorine is actually in the ortho position to the methoxy group, but in the product it is in the meta position. So there is a change, isomeric product is being formed. We will see why these type of products are being formed. So in this elimination addition mechanism, what happens is the first step is the strong base abstracts a proton from the aromatic system. So an anion is generated in the aromatic system. The leaving group leaves with its pair of electrons. The flow of electrons occurs from the negative charge. So we get a triple bond. So instead of a double bond, we are getting a triple bond. So this type of intermediate is called a benzyne intermediate. And this benzyne intermediate has two reactive centers. One is at this carbon, another one is at this carbon. So this OH can attack this carbon, or the same OH can attack this carbon, leading to two products. So that is the reason we get 1:1 mixture of two isomeric products are formed in the elimination addition mechanism. If we take this anisole derivative, there is only one proton that can be removed, and this leads to a substitution reaction. And here what happens is the addition occurs exclusively on the meta position to the anisole. See, there is a sigma bond is formed by the overlap of 2 sp2 hybridized orbital. So this is actually happening perpendicular to the already existing pi bond. So this is called the side by side overlap, and this benzene is very weak bond. Although it is a pi bond, this bond is very weak compared to this pi bond which is already existing in the aromatic system.
Now if we look at the reactivity of aryl halides and alkyl halides, aryl halides always react relatively at a lesser rate compared to alkyl halides. We need to find out what is the reason for this. Now, the major contributor for the poor reactivity of aryl halide is the resonance delocalization or resonance stabilization. Aryl halides are basically stabilized by resonance. We will see that how the resonance comes. And the second one is the difference in the bond dissociation energy. In the case of aryl halides, we have a sp2 hybridized carbon. In the case of alkyl halides, we have a sp3 hybridized carbon. So in other words, there is a different bond breaking energy involved in the case of alkyl halides and aryl halides. Due to the difference in the bond breaking energy, the reactivity is different. So here we have shown the Dewar structure or the Kekulé structure of chlorobenzene. So chlorine is having lone pair of electrons. So this lone pair of electron is given to the carbon halogen bond, which results in the formation of a carbon halogen double bond. So this is the resonance delocalization we were discussing about. This leads to a double bond character between C and Cl bond. So this leads to a negative charge on the ortho carbon. This undergoes resonance, and we can write all the resonance structures as shown here. So overall we can write the negative charges on the aromatic ring, and there is a chlorine having a positive charge. So this is a C double bond X. The X may be chlorine, bromine or iodine. So due to the formation of the C double bond X, the aryl halides are less reactive. And if you look at the bond length, the CH3X bond is, especially here the X is halogen chlorine. If we assume it is 1.77 angstrom, this is a sp3 hybridized carbon, whereas in the case of chlorobenzene, the X is chlorine. The bond length, CX bond length is 1.69, which is shorter than this 1.77 CH3X bond. So that means here we have a sp2 hybridized carbon, and this sp2 hybridized carbon have a double bond with the halogen. So that is the reason we have a shorter bond length. We know longer bond length, the bond energy will be easy to break. Shorter bond length will have higher bond dissociation energy. So if we look at the average bond energies, here we have given the bromo derivative as an example. So alkyl bromine bond has 68 kilocalories per mole, whereas phenyl bromide has a 70 kilocalories per mole. Bond breaking, bond dissociation energy. So these are all the reasons. This is having a higher bond dissociation energy. So aryl halides react very less compared to alkyl halides. Now the next major question we have to answer is why aryl halides do not undergo nucleophilic substitution reaction by SN1 or SN2 pathways. So what is an SN1 mechanism, which is very difficult for aryl system, because the carbon is sp2 hybridized in the case of aryl halides. So that means a sp2 hybridized carbon having a plus charge is highly unstable. And moreover, the CCl bond is very strong because there is a dissociation of Cl minus is therefore very difficult. If you look at here, we have a CX double bond. So that means this X is very difficult to leave as a X minus. So that is the reason This cannot undergo reaction by the SN1 mechanism. And another major, if the X is lost as a X minus, say for example if the X is lost as a X minus in this particular case, so this carbon which is a sp2 hybridized carbon will have a positive charge. So we call that as a phenyl carbocation, and that is extremely unstable. So these are all the reasons aryl halides cannot undergo reaction by SN1 pathway. Then what about the SN2 pathway? SN2 pathway also does not occur because, as we mentioned, the CCl bond is very strong. So a nucleophile cannot come and attack from the rear side to remove it, because this is a double bond and not a single bond. And because of the presence of sigma star orbitals, the middle of the ring, the nucleophile cannot come and attack. So that is the reason the rear side attack is not at all possible in the case of aryl systems. So the only thing possible is SN-AR mechanism, and as we had seen, the nitrochlorobenzenes can undergo nucleophilic substitution efficiently compared to unsubstituted chlorobenzene. So the presence of electron withdrawing groups, either ortho or para to the halogen atom, facilitates SN-AR mechanism. So these are all the reasons the SN1 or SN2 pathway is not possible for aryl halides nucleophilic substitution reaction. It does not mean that the aryl halides does not undergo nucleophilic substitutions. Aryl halides also undergo nucleophilic substitution, but the reaction pathway is little bit different, and it is not SN1 or SN2 pathway. Now you need to understand the difference between reactivity and the reaction mechanism. So far we have been discussing about reactivity. Aryl halides do not react as efficiently like alkyl halides. And we also have seen the SN1 and SN2 reaction mechanism does not operate in aryl halides. So what is the major difference between reactivity and reaction mechanism? So this is a crucial thing you need to understand. So the reactivity is basically, let us assume your house is at one place, you have to reach your destination, that is at a far off place. So the reactivity is basically the time required for you to reach the destination from the starting point. So in other words, the time required to reach from the starting point to the end point, that is what is called reactivity or reaction time, basically we can say. If you reach very quickly, then we can compare it like the reactivity is very high. If it takes longer time to reach the destination, then we say the reactivity is very less. And what is this reaction mechanism? The reaction mechanism is little bit different. Say for example, you can follow a path as shown here, path A or path 1. You can also follow another path as shown here. You can follow a different path, the third path like this, or you can follow path 4. So we have 4 different pathways to reach the same destination. The starting point is same, the end point is same, but the pathways are different. So these pathways are nothing but called as the reaction mechanism. So in effect what we can say is we start from the same starting material and we end up with the same product. The time taken to reach from the starting material to the end product is called related to reactivity. So in other words, how fast you reach the destination, that is what is called reactivity. And how many reach the destination? If there are 10 people starting from here, does all the 10 people reach the destination? Based on that we can say the reactivity is very high or very low. Whereas which path they follow to reach the destination is defined by the reaction mechanism. So in this particular case, if the person does not follow this particular path, we cannot say that the reaction or the person will never reach the destination. The person can follow another path as shown in the pink, or they can also follow the one which is shown in the blue color. So the path may be different. The starting point and the end point may be same. So the reaction mechanism is very similar to that. The path by which the destination is reached is called the reaction mechanism. So don't get confused between reactivity and reaction mechanism. So the reactivity is basically for the product formation. The path is reaction mechanism. Now let us continue with our study. Bimolecular aromatic nucleophilic substitution, which we saw as a SN-AR mechanism. So how this reaction actually proceeds? The halobenzene is reacted with the nucleophile. So this is the rate determining step. In other words, this is the slowest step because the aromatic ring itself is electron rich. The nucleophile is also electron rich. So there is going to be repulsion between the electron rich aromatic ring and the electron rich nucleophile. That is the reason this rate determining step is always very slow. So once the nucleophile attacks the halogen, that is the ipso carbon, then we end up with this particular intermediate. We can draw the resonance stabilized intermediate as shown here, and this loses the halide ion to give the nucleophilic substituted aromatic system. So in the case of SN2, this is a single step intermediate where the incoming nucleophile and the leaving group are both attached to the central carbon atom. This is like a penta-coordinated one. So in the case of aliphatic system, we have this kind of intermediates. Whereas in the case of aromatic systems, we have a tetrahedral carbon. That is, this carbon is having 4 groups, 1, 2, 3 and 4. So this is a tetrahedral carbon. So the tetrahedral intermediate is involved in the aromatic nucleophilic substitution. Now if you look at the potential energy diagram, in the case of alkyl halides, we have there is only one peak. In other words, there is only one high energy state in this particular reaction. So the nucleophile comes and attacks the carbon bearing the leaving group from the opposite sides. We get the intermediate as shown here, which is a high energy state. This loses the leaving group to produce the nucleophilic substitution product. So this is the high energy state, this is the lowest energy or the most thermodynamically stable product, and the starting material is shown here. And in the case of aryl halides, the starting material is shown here, and there are 2 high energy states and 1 low energy state. So in the first high energy state, the nucleophile, the incoming nucleophile forms a very weak bond with the aromatic halogen. And in the intermediate, which is a stable one, we have both the nucleophile and the leaving group are attached to the tetrahedral carbon in the aromatic system. And now the aromatic system and the halogens bond is weakened as shown by the dots here. That means the leaving group is ready to leave now. And finally the leaving group is lost as a X minus, and aromatic nucleophilic substitution had taken place. So this is how we can explain the potential energy diagram for both the aryl halides and alkyl halides. So here we have one high energy state. Here we have two high energy state and one low energy state. So this is what is called the intermediate. In this particular case, we do not have an intermediate. We only have a transition state. So generally the peaks are called as transition states and the troughs are called as intermediates. Now let us compare the nucleophilic substitution between alkyl and aryl systems. So in the alkyl case we have SN1 mechanism. The Rx is dissociated into R plus and X minus. So a carbocation is formed, and this carbocation is attacked by the nucleophile to give the RZ, that is the final product. And in the case of SN2, the nucleophile attacks the carbon from the opposite side of the leaving group. We have RZ formed with the removal of the leaving group. So here little or no charge on the central carbon atom. So this is a no charge intermediate. Here we have a charged intermediate, which is a carbocation in the case of SN1. And in the case of aryl systems, we have a negative charged tetrahedral intermediate as shown here. So there is a negative charge on the aromatic system, and this is a tetrahedral carbon. So here we have a negative charged intermediate that is formed. So this is how we can actually compare the three different pathways for nucleophilic substitution reaction. And let us compare between SN2 mechanism and SNAR mechanism. So in the case of SN2 mechanism, there is no evidence for any intermediate formation, whereas in the case of SNAR mechanism, we have something called Meitner-Heimer complex, which is the tetrahedral intermediate we have talked about, that can be isolated. So this is a isolable intermediate. So we can say this SNAR mechanism follows a Meitner-Heimer or the tetrahedral intermediate formation. And in the case of SN2 mechanism, we know it is a rear side attack, so the product obtained is always having an inversion of configuration. Whereas in the SNAR mechanism, it is a front side attack, so there is no inversion of configuration because there is no chiral center in the case of aromatic systems on the aromatic ring. And the major difference is in the case of reactivity order, fluorides react very slow in the case of SN2 mechanism, and iodides react very fast, whereas in the case of SNAR mechanism it is exactly the reverse. The fluorides react much faster compared to iodides, and SN2 is basically a single step mechanism, whereas SNAR is basically a addition elimination mechanism. In summary, let us recap. We have studied about the various preparations of aryl halides, which includes direct method of aryl halide formation. From diazo compounds, how we can prepare aryl halides. And we also studied about the Hunt-Sticker reaction. And in the reactions of aryl halide, we studied about aromatic nucleophilic substitution reaction, that is basically SNAR mechanism. We also have studied about addition elimination and elimination addition mechanisms which are employed for the aromatic nucleophilic substitutions. We also compared the reactivity between alkyl halides and aryl halides, and why SN1 and SN2 type mechanism doesn't operate in aryl halides, that also we have studied. So we also have studied various evidences that point towards the SNAR mechanism. With this, we conclude this session. Thank you.